Welcome to one more lecture on CVT, complex variables and transforms, and in this lecture we'll start studying Laplace transforms. Laplace transform is a transform that is applied on a signal that we find in time domain, and we move to a domain, we call it S domain, where only have the variable S instead of t. And the transform is computed using this integral based formula, where the given function of time is multiplied by e to the minus st and is integrated from 0 to infinity, right? And this transform is defined for the values of t greater than or equal to 0, greater than or equal to 0, right? So let's solve an example where we are given a unit step function. A unit step function is a function that has value 1 for all values of t after time t is equal to 0 and is 0 otherwise. So it is 1 for time t greater than or equal to 0 and is 0 otherwise. So let's plug this value f of t in this formula. 1 times e to the minus st dt, we integrate from 0 to infinity. The rest of the computation is very simple. 1 times e to the minus st is e to the minus st. We go from 0 to infinity, and if we integrate, it comes out to be minus 1 over s times e to the minus st, and the limits are from 0 to infinity. We put the limits. E to the minus infinity is 1 over e to the infinity, and this is 0 minus 1 is minus 1 times minus 1, so 1 over s. So Laplace transform of 1 is 1 over s, and of course for a constant k it would be k over s. Next we see the Laplace transform of e to the minus e to the plus at, and of course for t greater than or equal to 0, right? What we do is we replace this f of t with our new value e to the at, and the rest of the formula remains the same. So it's e to the at times e to the minus st dt, and we take t common, and the rest is e to the a minus s, or we can also write it, we're taking minus common, is e to the s minus a plus s, or s minus a. So if we integrate, this comes out to be minus 1 over s minus a to the minus s minus a t, plugging the values of infinity and 0 the limits, and it comes out to be 1 over s minus a. So lambda Laplace transform of e to the at is 1 over s minus a, right? There are some interesting properties of Laplace transforms. One of them is linearity. If we have two functions f of t and g of t, and we are asked to compute the Laplace transform of their weighted sum, where f of t is weighted by a and g of t, the other function, is weighted by b. So it can also be written as a times Laplace transform of f of t plus b times Laplace transform of g of t. So a can be taken out of the Laplace transform. Similarly, b can also be taken out, and this plus this Laplace transform can be distributed across this sign. So this is the linearity property. Let's see what are the benefits of this linearity property. Let's find Laplace transform of cos hyperbolic at. Cos hyperbolic at can also be written as e to the at plus e to the minus at divided by 2. Applying this property, the linearity property, on this function, this is 1 by 2 Laplace transform of e to the at plus 1 by 2 Laplace transform e to the minus at. So we know e to the at, the Laplace transform is 1 over s minus a, and for e to the minus at, this is 1 over s plus a, because we have replaced a with the minus a. So this, if we replace a with minus a here, this becomes s plus a. So adding this, taking the LCM, s squared minus a squared times 2, and then solving gives us s over s squared minus a squared. So let's see one other example of the linearity property. Laplace transform of sine hyperbolic at. Sine hyperbolic at can also be written as e to the at minus e to the minus at divided by 2, whereas cos hyperbolic AT is this plus, so the differences of this sign. The sign is negative here, minus in case of sine. In case of cosine, this is plus. Alright, so once again we apply the linearity property, and this is 1 by 2 Laplace transform v to the AT minus 1 by 2 Laplace transform v to the minus AT, and then taking the LCM and then solving gives us this. Right, that's all for this lecture. In our next lectures we will keep on studying more about Laplace transforms. Thank you.